Okay, so it says a cylindrical drill with radius 5 is used to bore a hole through the center of a sphere radius 7. Find the volume of the ring-shaped solid that remains. So we've got this. Ready to start? So we got this kind of physical situation, and we have to figure out how what we're working on applies, how we model this with the mathematics that we're learning, right? So I've got a cylindrical drill, sphere of radius 7. So that's kind of easy to model. What's the easiest sphere of radius 7 we can model? So center, radius, what should we do? He said x squared plus y squared plus z squared equals 49. Is that the easiest way to model a sphere? Because its center is origin, right? Yeah, so that's a good sphere of radius 7 to pick. So this is up to you, right? We're using the mathematics. We're creating the mathematics that's going to model this situation. They didn't give us any equations. They didn't say use R3, use polar, use you have to have the mathematics at your in your toolbox to model the situation. So we're going to start with a sphere of radius 7. Best sphere I've drawn all day. So we'll just do that, and and would you agree we could just do the top half and then multiply by 2, right? So we could just do half of this and multiply by 2. And why is that helpful? Why is doing the top half helpful in terms of the mathematics that we know?
Because you have to do two integrals, just like plus or minus, if you would want to solve for z.
Yeah. So what does a double integral find? It finds what? Net volume to where?
Under.
What's that?
Net volume of the line area.
No.
The xy plane.
To the xy plane, right? It's the net volume between our surface and the xy plane. Net volume between our surface and the xy plane. So that's why a half sphere is really convenient. Why? Because we could put the half at the xy plane. And this matches what we know about double integrals. Okay? And so where do we want to bore this hole there then? Where are we going to put the hole? Yeah, so make the center of the cylinder the z-axis. We know we can do that real easily. So like this. So we're going to bore out like that. And now I want the volume. So if we do the double integral to find volume, it's going to be the double integral of what? Double integral of what? So there's two aspects, right? What's the function we're going to do? And what's the region we're integrating over, right? Those are the two aspects we've been working on with double integrals. So again, we're trying to model this situation with a double integral. What's going to be the function?
Your half sphere minus the cylinder.
He wants half sphere minus the cylinder. What do you think? Agree with that?
Just be a half sphere, right?
Just the half sphere.
Oh.
Are you changing your mind?
Yeah.
Because the cylinder is what? It's kind of it's determining laterally like what happens here. And so really the whole top of this is the sphere. Do you see that? The whole top of the thing we're trying to do is the sphere. And we want all the volume from the sphere down to the xy plane, right? But not inside the red cylinder. Does that make sense? So then therefore this should be what? So if we're saying f of xy, what is going to be our f of xy, our function that we're integrating? Yeah, so this is essentially z, right? Function values are z. So we're going to solve this for z, right? there would be a lot for you to figure out here, right? As terms of modeling this situation with mathematics. So our function values are z, and so z is square root of 49 minus x squared minus y squared. So that's the surface that we're integrating. And now the last thing is the region, right? So what are our bounds of integration that we're going to need? And what kind of problem is that? When we're determining bounds of integration in a double integral, what general type of problem is that? Geometry problem, right? Geometry. So it's the geometry of what? Geometry of what? In the xy plane, right? Or we're deciding like laterally what's going on here, or which part of the sphere are we picking to integrate, right? That's what the bounds of integration are saying. We're saying what points on the sphere are we deciding to integrate, and we'll give those as xy points. So which points do we want to integrate or get the volume below? What's that? Circle? A circle's not a region. Area of the circle? Just like inside a whole circle like that? Between two circles? Yeah, it's going to be outside of the red. The cylinder is going to be like the outside of that red cylinder, and then inside of the circle that you get when the sphere hits the xy plane, right? So it's going to be like in between. I should have drawn green and red. Oh well. So don't we want to integrate that top of that sphere kind of over this washer, this ring, solid ring? So that's going to determine our bounds of integration. So now we have decision, type 1, type 2, or polar. Right, they all say in chorus, right? Of course, this is definitely going to be a breeze in polar compared to trying type 1 or type 2. Can be done, but it's going to be lots of square roots and breaking it up. But this is like, this is right in the wheelhouse of polar. Right in the wheelhouse of polar. Okay, so we're going to change this to polar, which means we got to change the function to r and theta. What will it be? Square root of 49 minus?
R squared.
Yeah, so you can do r cosine squared and r sine squared, but then in the end, it's just going to be minus r squared. dA is r dr d theta. And we're going to go, r is going to go from what to what? 5 to 7, radius of 5 to radius of 7. We're looking at the picture here, 5 to 7. And theta from? We got it. But there's a lot, you have to really understand double integrals really well to know how to set it up to model the situation, because they didn't give you any, they just gave you this physical situation, and you have to see how a double integral applies to it. Okay, this antiderivative, you could use U-substitution, or you could just recognize this is kind of like the result of a chain rule, right? Where this is essentially the derivative of the inside of that. Right, this is like chain rule, G prime F times F prime. And what are we trying to find? We're trying to find G of F. So what would that be? 49 minus r squared to the? This is to the 1/2 power, so 3/2, right? And then we need a 2/3. What else do we need? Not just 1/2. Negative 1/2, right? We're going to need a negative 1/2 for the minus r squared and a 2/3 for the 3/2. And then we're home free. Okay, any questions on this? Does it help? Any questions? Okay, let's look at just talk about one more here. Can I erase what's up there? Cool. No. was it? This one. What was this? Okay. So the solid shape, like an ice cream cone, bounded by the functions z equals square root of x squared plus y squared. What's that? Z equals square root of x squared plus y squared. It's a right single cone, right? Because it'd be z squared equals x squared plus y squared, but only the plus positive of the square root. So we've got that. And then, what's this? Z equals 32 minus x squared minus y squared. Recognize that? Sphere, radius. Square root of 32 is the radius, right? So we're going to have a sphere coming in like this. And then this. Something like that. So we need what? We need the volume of the ice cream cone. So the volume of the ice cream cone, they're talking about what? Is that above or below the cone? And above or below the sphere? Below the sphere and above. So it's all this stuff in here. So does that go all the way to the xy plane? No, it doesn't. So just a double integral of a surface is not going to do this, right? So we've got to be have a little more ingenuity here. How can we get the volume of what I've shaded? This is pistachio ice cream. Pistachio. Okay. So how can I get the volume of what I've shaded there in this lovely green? Yeah.
Sphere minus the cone.
Okay, sphere minus the cone. Because if you did the sphere, this is an important thing to recognize. If I integrated just that spherical cap right there, what would I get? I get the volume like of a silo kind of, right? Like all the way down to the xy plane. If I did this, if I just did the sphere. And then if I subtract the cone, then will be everything below that to the xy plane. So by subtracting out the double integral for the cone from the sphere, I'm going to be left with the ice cream cone. Do you see it? So that's just talking through what that one is like. Any questions on that? Okay, so let's do it 7 tonight. On Monday I posted the written homework for tomorrow. It's a shorter one. Should be pretty straightforward. It's easy compared to what we're doing now. So that you should be able to do that. And then we're just WebWorks every class period. WebWorks 7 o'clock after the next class. Ready to start? New stuff? So just when you thought you were safe with double integrals, triple integrals. Now it's getting good. Here we go, triple integrals. Okay, so this will all be on the video. So rather than trying to recreate all these pictures, because things will it's like this, things change as I go, and so it's gonna be hard to take notes. Just really listen and try to absorb this, and then take the notes from the video later where you can pause it. Okay, here we go. So here's a triple integral. This is what they look like. So this is a multivariable function of 3 variables. Where do those live? Where do multivariable functions of 3 variables live? R4, right? So they call these like hypersurface. They live in R4. Tough to depict on a 2-dimensional surface, but there's been different ways that they've tried to do that. We won't, okay? But you just know this is a 4-dimensional function, so it lives in 4-dimensional space as what they call hypersurface, okay? And then what we're integrating over then is going to be, so what do we integrate over in a double integral? It was what, a region in R2, right? So now we're going to be integrating this hypersurface over what? A solid in R3. So that we can draw, right? And we said these are geometry problems, so we will be drawing those in terms of analogous to our R2 pictures before for double integrals, which is like the region. So we can still draw these solids, which are determining the limits of integration. We can draw those, but we're going to stay away from the hypersurface. Okay, so here's the general idea with this. We're going to think about these as for surface to surface. This is in R3, right? We're doing the bounds for a triple integral. Those bounds are geometry configurations in R3. And we're going to start with surface to surface. And then we're going to take our solid and we're going to project it into a coordinate plane, and we'll get a region in the coordinate plane, and then we'll set up a double integral for that region. So that's the way to think about all triple integrals. First, surface to surface, then project the solid into a coordinate plane and do a double integral. So it's not a three-step process, it's a two-step process, okay? Think of it in two steps, not in inside integral, then second, then third integral. Think of it as a surface-to-surface integral, and then a double integral for a region. Okay, so here's type A. So type A, notice what we've got. You've got a lower surface and a higher surface. So this is the surfaces that we're most comfortable with. Z is a function of x and y. So when we do the inside integral, it's going to be, so first of all, the first limit that we're going to work on is dz. dz, up and down. And so we're going to go from surface to surface, and what will that be? That will be from bottom surface, the green one, to top surface, the blue one, or bluish. And then, so once we establish what the bottom surface is and the top surface is that makes up this solid, then we're going to take that thing and project it into which plane? So the picture shows it. We're going to project it into the XY plane. And then we'll do our double integral for that region, which we've already learned, right? We know how to do that. Yeah? Just these. The top one, the blue one, is H2 of XY, and the bottom green one is H1 of XY.
On the picture.
I know, but that's what these are. Just ignore the picture.
Oh.
Write these. Yeah, that's what these should be. Those are functions called H. H1 and H2. Okay, so that's what we're going to call a type A triple integral. That's where you do Z first. You go bottom surface to top surface. You project that thing into the XY plane, and you do your double integral on that projection. Does that make sense? Okay, so here's type B. So type B is going to be, first of all, what's going to be our, looking at the picture, what's going to be our first variable for integration? Instead of dz now, we'll have what? He wants dx. Agree with that? Is that what the picture shows? Dx first. Which means what surface to what? You're going from what to what? We're going to call that back. That's the green one. To front, the blue one. Back to front. And then our outside double integral will be projected into which plane? YZ plane. That's the gold D region. Does that make sense? So the last one's going to be, look like this. Type C. What's our first variable of integration? dy, which means, so it's going to be dy first, which means we're going to go from what surface to what surface? Left to right, right? The green one is the left surface, and the blue one is the right surface. And then we're going to take that solid and project it to which plane? xz plane and do the double integral in the xz plane. Getting the idea of this? So now this whole thing describes a type C triple integral. Yes, sir?
You said back to front.
Yeah, back to front. So lowest x value to highest x value. Yeah. So when we do these double integrals, we set them up as type 1, type 2, or polar in any of the planes. Polar in any of the planes, not just xy plane. So that ends up meaning that there's actually 9 different ways to set up a triple integral, right? Type A, and then the double integral type 1, 2, and polar, etc. Type B, 1, 2, and polar. Type C, 1, 2, and polar. We're having fun now. No, these are really cool problems. If you like geometry, this is fun. All right, here we go. So that's the overview. So let's do an example. So I've got this tetrahedron. It's a four-sided, has 4 sides, 4 vertices. All the sides are triangular shape. So we want to write the triple integral f x, y, z over the tetrahedron with vertices. These are the vertices. And when I say 6 different orders, now we're saying don't worry about polar, right? So the 6 would be A, B, and C, and then in each of those, type 1 and type 2 double. So the first thing we need to do is we need to get the equation of, get this surface as a function, right? So there's actually 2. 2 surfaces, well, there's 4, but 2 are very easy. So there's this triangular surface here, this underside here, there's kind of this left side here, and the back there. So we need functions that describe those 4 surfaces. So I'm going to do attendance and just get as far as you can with those. So the one that takes the most time would be this one right here. That's the most most involved. So this is our 004. This is 030. And this is a 201. So let's just, for sure, work on that. How can you get the equation of that plane? We need the equation of that plane in R3. So that's just a blast from the past. Remember I told you not to forget anything? But you can work together, okay? So you're going to try to get the equation of that plane that includes those 3 points on it. Okay? So you're either making progress or you're getting help. Okay. First step. What's that? So we need a normal vector to that plane. How are we going to get a normal vector to that plane? Okay, cross product of what? So you're kind of starting from you're going backwards here. So cross product of what?
You need like the 2 vectors on the plane.
So right, so we're first going to write 2 vectors parallel to the plane. And how do we get those? Point to point, right? You've got lots of choices here. So you can make one like this. So final minus initial, right? What would that be? -2, 0, 3, right? And write another one. Say this one. Again, lots of choices here. Then what? Cross product. Cross product gets you what? That gets you the normal vector to the plane. And then pick any point you want, and what do we got? A times x minus x naught, b times equals 0. Remember that? What's our normal vector? ABC, right? Normal vector is ABC. Any points you want on the plane, choose any one you want, x naught, y naught, z naught. And then what's x, y, z then? What's the x, y, z? That's it represents any and every point on the plane, right? They're gonna stay x, y, z, and any ordered triple x, y, z that makes the equation true is a point on the plane. Okay, questions on that? So you do all that, and here's what you get. Did anyone finish it? I got z equals negative 3/2 x minus 4/3 y plus 4.
I didn't solve.
Okay, but if you did, would you get that? You should. So when you do all the math and solve for z, that's what you should get. And I'm just going to call that generically, I'm going to call that z1. I think we can just leave that up here. So I'm going to call that generically z1. And then if I solve that for y, I would get this. You'll see why we're going to do that in a second. Exact same plane. Solve for y as a function of x and z. And then, finally, solve for x. And you get that. So I'm going to call these, just for namesake, and we don't have to keep rewriting this, z1, y1, x1. These are all the same plane, just written as 3 different functions. Z is a function of x and y is a function of x and z, etc. And which plane is it? It's that plane that shears through all the axes. Okay, what about this one under here? So notice that goes through 0, 0, 0. Is it 0, 3, 0, I think? And 2, 0, 1. So what plane is that? That's a lot easier. Do you see what plane that is? So then also it will go through, what, 2, 3, 1. That's not part of the tetrahedron, but that plane goes through that point too. So what is that plane? What's always true there? You see that has the y-axis in it, and it's basically what? It's like a cylinder. It's like a planar cylinder, right? So you could just take whatever the equation of this line is, extend it in the y direction, and you get that plane that's underneath there. So what is the equation of this line? Z is equal to 2x, right? 2x. Isn't that right? I'll call that z2. And then so x2 is 1/2 z.
Shouldn't it be x equals 1/2 z?
Yeah,
Yeah.
yeah, so either z is 2x or x is 1/2 z. So that's the underplane. So you can just kind of figure that one out. All right, any questions? That's the setup. So now we're ready to start writing some integrals here. So I want to do this. I want to do the most natural one first. And that's type A. So type A means? What's our mantra for type A? What? Bottom surface to top surface, which is the variable what? Z. We're going to do, it's going to be dz first. So just some generic hyper function that we're integrating. We don't care about that right now. But we're going to do dz first. And so what's that? That's bottom to top. So here's how I suggest you think about this. Imagine an archer. If it's bottom to top, the archer is below the solid and he's firing his arrow into the bottom of the solid, and then the arrow's going to go through. It's going to enter in the bottom and leave out the top. So that's how you can figure out what the bottom and top surface is. So where will here's the archer down here. And he shoots. And it enters in the bottom. What is the bottom surface? Z2, right? Isn't it Z2? And that's what is Z2? 2x. And then does it always enter in Z2 no matter where the archer is? Is that always the bottom for the whole solid? Yep. And then where does the arrow leave? Z1, right? Does it depend? Does it depend? Or does it always leave out Z1? So here's how we can tell. We can look down, straight down on it. Watch. So if you can't tell, we can look down on it. So does it always enter in Z2 and always go out Z1? Yes. See that? So I could write Z1 here too, but it's not. Yeah, let's just write Z1 here. But what we would normally write is all that. That's what Z1 is. Because we're going to have x's and y's later in the problem, so we need all those x's and y's. Okay? So when I write Z1, that means you would write all this stuff right there. Okay, so now what's next? So we got bottom surface to top surface. What's next? We're going to take the solid and project it into the xy plane, and then take that region that we get and do a double integral. Type 1 or type 2. All right, so let's take a look. So all I need to do is look down the z-axis, or if you don't have the ability, so you would project all these points. Project this point down here. That point's already in. That point projects there. So what we get for the projection is, in the xy plane, is this triangular region. Do you see that? I'm going to show it to you a lot cleaner, but that's how you do it without the software. Take all the points that are the corners and let them fall to the xy plane, and then those corners will determine the region. So let's take a look at that. Got it. So that's my projection into the xy plane, looking down on it now. And so I'm going to do a type 1 integral. Type 1 means go from bottom to top, left to right. So I'm going to do dy. So this is type A1. Bottom to top, left to right. So what's the bottom? Y equals 0. Top is. So now we can come here and take this point. What was this? This was 0, 3, right? Just take the z coordinates off. And this is 2, 0. Z coordinates are gone because all the z coordinates just fell straight to the xy plane. So now we can write the equation of that line. What is that? 3 minus 3/2 x. So we're going to go from 0 to 3 minus 3/2 x. And x goes from 0 to 2. It's double integral now, right? So think of it in two parts. Surface to surface, double integral of the projected region. Questions on type A1? All right, we're going to skip A2 because A2 is going to have the same z, and then you're just going to do the other, you're just going to reverse. You got lots of practice going dx dy now. So type A2 we'll skip. So the key is this is the same. dz first, and you're still going to go from 2x or z, or what we call z2 to z1. But again, when you solve this problem, if you were to do this, actually do this triple integral, you're going to have the x's and y's in there, right? You need the x's and y's in there, but for clarity, I'm not going to write all that out. Okay, so how about, what should we do next? I'll give you a practice problem here. So why don't you try, see if you can do type C. C2. See if you can do type C2. See how that goes. So when I say type C2, what will the order of integration be? D what? D what? D what? So determine that first. What will your order, if I say type C2, what will the order be? Determine that first, and then think of it as surface to surface, double integral, type 2 double integral. To surface. Which surface to which surface first? Bottom, top, left, right, back, front. He wants left to right. Agree? So where's the archer? Here. Here comes the arrow from the left. What's the left surface? Y equals what? Where this thing pierces in. He suggested y equals 0. Agree with that? Be this surface over here, right? Y equals 0? Some people are nodding. Yes, y equals 0. That's the XZ plane, right? Isn't this triangle here is the XZ plane? Okay? Enters in there. Does it always enter in there? Yes. Okay, where does it exit the surface? So the right surface. It exits this slanted plane, right? And so we need y in terms of x and z, which we did. That's y1. Normally you would write all that out right there. But for clarity's sake, I'm just going to leave it here. So you'd write this whole thing out right there with the x's and the z's in it. So we're going from 0 to y1. Then what? We're going to project this solid to the XZ plane. Can you imagine or sketch that? Can you imagine / sketch that? You need to be able to make a sketch, right? So you won't be able to turn it like me. So when I turn it in class, it really helps. But eventually, you're going to have to imagine and sketch that. So are you imagining and being able to sketch this? There's our projection into the XZ plane. Is that what you were thinking? Hopefully that's what you were thinking. So now we're going to do dx dz. What does it mean? If I do dx dz, left to right, and then bottom to top. Okay, so what happens? So what's the left? I think this do have, and this would be 0, 4. So again, now the y coordinates are gone. You just drop the y coordinates. Drop your pen too. Drop the y coordinates. I didn't plan that. All right. So you just drop the y coordinates so that those ordered triples become 0, 0, 2, 1, and 0, 4. So I'm going to go, what's the left side? 0. What's the right side? Oh, ye experts of double integrals. What's the right side? Depends. It's split up. You should see that. That if z goes from 0 to 1, this is the right side. When z is going from 1 to 4, this is the right side. So this is z is... Did I have this wrong?
That's what I'm saying.
How was I blowing that? So it was 2, 0. What's the point? 2, 0, 1? Yeah. Yeah, I totally blew that. Z is 1/2 of x. It's not z is not 2x. Z is 1/2 of x, and x is 2z. John was the only one having trouble with that. Maybe others too, but in a good way. He was the one having trouble with my problems. So this is z equals 1/2 x. And this is z equals 4 minus 2x. Not 2. What's that rate of change? 3/2 again. Minus 3. Yeah, 3/2, right? So what does this mean? To do a type C2, we have to? We're going to have 2, but the inside dy is the same, right? That's not going to change. What changes is the outside double integral. So we'll still have 0 to y1, but sometimes we go from 0 to 1/2 x. Okay, but this is x. X needs to be written in terms of z. So this is x equals 2z. And this is x equals negative 2/3 z minus 4. Is it right? Do it in my head, trying to do my head fast here. 4. Yeah, or you can do positive 2/3 4 minus z. So either negative 2/3 z minus 4 or positive 2/3 4 minus z. Both work. All right, so 0 to y1. At the bottom, when z is between 0 and 1, x goes from 0 to 2z. Right? And then this is just the double integral now. When z goes from 1 to 4, that's when x is going from 0 to that thing. Same function. So this particular triple integral means the surface to surface is the same, but when we get to the double integral, it's split up. So then the outside double integral will be different, depending on z. Z goes from 0 to 1. We go to the lower diagonal line. When z goes from 1 to 4, we're going to that one on the right. Okay, as you're packing up, if we do a type B, what's going to happen? So here's looking right down the x-axis. When you do a type B, back is x equals 0. What's the front? Split. When you type B, you get a split because of the inside integral. Sometimes the arrow comes out x1. Sometimes the arrow comes out x2 down here. So we're going to have a split, but now the split is different because of the inside integral for type B. Maybe we'll do that at the start next time.